No, I will share. I will do it right now while.
Okay,
Because it's on. There's no email.
okay. Maybe we should.
Okay, just a moment.
Yeah, just put it on your name.
No, should be fine like this. Let's try. Okay.
Good morning, everyone. Welcome to the second session of the Wealth Network. Our first speaker today is Francesca Peluzzi from Pianar.
So thank you for your presentation. So again, my name is Francesca Peluzzi and I'm a researcher in Italy. Currently, I'm working at the Italian National Research Center. And today I'm going to talk about a very recent work that born from a long-lasting collaboration between my own institution and the University of Rome Tor Vergata, in particular Professor Roberto Benzi and Mauro Sbragaglia. And this work focuses on the transient dynamics towards the convective state and the phase inversion in yield stress emulsions. So first of all, what I show will be okay. Okay, perfect. Perfect. So first of all, I will give you an overview about the main properties of emulsions. Then I will describe the setup under investigation, that is the Rayleigh-Benard thermal convection. I will give you some details about the open access tier-defined code. That is an open access code I used in order to run this kind of simulations. And then I will go through results and conclusions. So first of all, what are emulsions? Emulsions are part of a wide class of materials called soft materials that we can find in our ordinary life. So here, for example, the form of a beer, the gel magma, and so on. And these systems and materials are part of the same class because they are characterized by common properties from both the structural and rheological point of view. So from the structural point of view, they are composed by multi-component or multi-phase systems. In the case of emulsions, we have micrometric droplet of a certain liquid component that are dispersed in another different liquid component. So we have two systems at the same phase but different components, oil and water, for example. Among the other properties, we have the rheological ones that are the most interesting one that we can summarize here. So with rheology, we mean the mechanical response of the systems to an applied external force. And this response can be drawn as a relation between the stress applied for unit area on the material itself as a function of the shear rate, that is the gradient of the velocity triggered inside the material upon the application of the external force. So as you can see here, in the case of emulsions, the rheology is complex in the sense that if you apply a stress that is below the critical threshold, called yield stress, then they behave in an elastic or solid-like way. Otherwise, when you apply a stress that overcomes the critical threshold, then they start to flow. And this behavior is well described by the phenomenological law of Herschel-Baltri, where, as you can see, the yield stress, so the critical thresholds, are pairs. So the very interesting part of this material is that the rheology, so again, the mechanical response of the material, depends strongly on the droplet concentration. It is defined as the fraction of volume occupied by droplets as compared to the total volume. So just to give you an idea, because we call it, the reason why we call it complex rheology, the reason is that if you have in mind just a simple homogeneous fluid like water, then you will have a rheological curve that is linear, as in this case. And this means that the viscosity, the dynamic viscosity is constant. Otherwise, in the case of non-Newtonian behavior, we have a viscosity that depends on the value of the shear rate. This is the difference and the reason why we call it complex rheology. And what happens is that if you consider a diluted emulsion like this one, then you observe that it behaves in a Newtonian way, like the water, so the case with no droplet. But if you still increase the number of droplets, then the rheological curve changes in a continuous way up to, for example, this rheological curve here, where there is still no stress, not yet, at least, but still the behavior is non-Newtonian because the viscosity depends on the shear rate. And then the most extreme case where the behavior is Newtonian, but the value of the yield stress is different from 0. So this is the landscape in terms of emulsions. And what we are interested is to investigate the dynamics and the heat transfer properties of these materials under the so-called Rayleigh-Benard thermal convection. In this setup, we have the material placed between two walls, a lower hot wall and an upper cold wall. So between the two walls, we have a linear gradient, at least at the beginning. The two walls are placed at the distant edge, and the system feels the action of the gravity. So if we want to describe this kind of system, we need the Navier-Stokes equation for the dynamics of the fluid, supplemented by an additional buoyancy terms that acts only in the direction of the gravity, and it is related to the value of the temperature, the local value of the temperature. And at the same time, we have the dynamics for the temperature itself. That is an advection diffusion equation, where the advection is possible to the velocity of the fluid. And we have this two-way coupling between the dynamics of the fluid and the one of the temperature. So if we want to investigate the heat transfer properties of this in this kind of setup, we measure the Nusselt number defined in this way that give us a sort of balance between the convective transport and the conductive transport inside the material. And to give you an idea, if we are considering, for example, also in the case of the water, simple fluid that is in a conductive state, so no convective role appears in this case, then this term here has no contribution, and the value of the Nusselt number is equal to 1. But if you increase enough the buoyancy force entering here, then you observe that a value of the Nusselt number increases as well. So in this game, there are two main players. One is the droplet concentration, and the other one is the buoyancy force. So the heat transfer properties are ruled by these two main parameters. In order to address these kind of simulations, we use the open access Lattice-Boltzmann field-defined code that is based on the multi-component Chern model. So we are performing 2D simulations with, first of all, the necessary interactions in order to create the phase separation of the two components, supplemented by some additional interaction that has the aim of mimicking the effect of the surfactants that are at the interface of in real system, in real emulsions, and they inhibit the coalescence of the droplets. So unfortunately, these two videos doesn't work on this laptop here, but the point was that only by introducing this mimicking of the presence of surfactants, then you can stabilize the emulsion and go towards very large values of the droplet concentrations. Otherwise, you will have at the end just one single big droplet. So it was extremely necessary. The idea is to introduce two probability distribution functions for the two components, and a third one ruling the dynamics of the temperature, and the three dynamics are all coupled together. This code was very useful because, first of all, from the point of view of the performance, it is GPU parallelized, so quite fast. And at the same time, it is supplemented with some additional Lagrangian tools that were necessary in order to characterize this kind of setup at the level of the droplet, so at the droplet scale. Okay. So in our previous work, what we investigated as a first analysis was the Nusselt number as a function of time at fixed buoyancy applied and changing the droplet concentration. And what we observed mainly is that when you reach a steady state or stationary behavior, then the average value of the Nusselt number decreases as the droplet concentration increases. And at the same time, the fluctuation of the Nusselt number increases as well. So the origin of this fluctuation has been deeply investigated in these two works, but this is not the aim of the present talk. What I want to talk about is what happens if we still increase the droplet concentration up to the emergence of the yield stress, as I told you before. So in this case, we are dealing with this complex rheology. We are considering yield stress emulsion, so this is the initial condition. it's very packed to be 2D simulations, so roughly 80% of droplet concentration. And by performing a dedicated rheological experiment, then we see that the value of the yield stress is different from 0, and we can also fit the rheological curve with the Herschel-Balfe A1. And this is what happens. It was very interesting and unexpected. So starting from this initial condition, both in terms of the emulsion, but also the linear gradient between the two walls for temperature. So it's just conduction at the beginning. If we increase the value of the buoyancy force, what we can see is that the Nusselt number, so our measure of the heat transfer as a function of time, presents a very interesting transient dynamics, where there is a succession of resting periods where the Nusselt number is equal to 1. So there is no motion in principle, no convection, but then something happens that triggers again the motion and the heat transfer associated. Each bullet here corresponds to the detection of one coalescence event, meaning that when the system is placed in motion again, then some coalescence events are triggered, and the system is changing from the structural point of view if you still wait the dynamics going. Then if you are patient enough, you will reach a stationary state in terms of the Nusselt number. And on this plot, I also report the number of droplets as a function of time, confirming the occurrence of coalescence event, since we have a drop in the number of droplets anytime we have a heat burst and coalescence event. So here it was too heavy to put it in the presentation, but if you want, you can pass my iPad in the audience and see the full video of the dynamics. That is quite slow. That's why I cannot plot it together here. But here I can summarize the dynamics. So as you can see, when you are in a resting period, then the situation, the temperature field is linear between the two walls, meaning that the system is in a conductive way. But after some peaks in heat burst, then a coalescence event appear, and the system is changing in time up to the case where it starts to be in a convective state. So the Nusselt number overcomes the value of 1. The emulsion is rupturing at that time, up to the end where you observe a partially phase-inverted emulsion. So you started from a highly packed emulsion, and then you reach a state where you have a mixture between the original emulsion and one that is phase-inverted and diluted in this case. So from an oil-water to a water-oil emulsion in this case. And all these dynamics with this mechanism in this intermittency cannot be captured just by considering the continuous equation and placing the rheological information or cut and paste them inside the equation itself. So simulations is necessary to investigate this kind of dynamics. Here, by comparing the rheology of the initial or original emulsion and the one phase inverted, we can see that obviously the rheology is complex at the beginning, but after this kind of changing from the structural point of view, then it reaches a linear behavior typical of a diluted emulsion. And it is almost or quite obvious since the phase inverted emulsions is diluted in terms. So what was very interesting to investigate was the origin. So how can the system start to be in motion again if our continuous equations do not predict the restarting of the motion? Because if in the case of the system persists in a resting period, then it has to be stopped there, so stuck in that condition. But we observe a restart of the moving. So in order to investigate the reason why this restart is possible, we use one of the Lagrangian tools available in TLB-Find that allows to identify the center of mass of each droplet, build the Delaunay triangulation, and by knowing every link between the droplets, we can detect the so-called plastic event, that is a topological rearrangement or a neighboring switching, anytime one link between two droplets shrinks up to disappear, and then a new one appears, as in this case. So by counting the number of plastic events as a function of time, we see obviously that there is a larger activity during the motion of the Martian, but there is a still activity also during the resting period. So they are not very resting because there is a kind of residual activity that allows the system to accommodate in the best structural topology in order to allow the system to move again. And this is further confirmed by performing a second analysis, again at the level of the droplets. So TLB Fine also have a tool to measure the Nusselt number associated to each droplet. So it's not a macroscopic analysis, but a mesoscopic one. And what we can observe by collecting the statistics is that obviously we have large tails during heat bursts, but the most interesting aspect is that the Nusselt number is different from one, and a lot different from one, also during the resting period, still confirming the presence of this residual activity. And finally, what was also interesting was to measure the droplet correlation function, in particular the displacement correlation function, as a function of the distance r between the droplets normalized with the average droplet diameter. And what you can see is that the correlation is large during the heat burst, obviously, because you have the thermal plume that occupies the majority of the system. So it's macroscopic and all the droplets follow the macroscopic motion. But what is interesting is that still in the resting periods, we have large correlation among the droplets due to this local rearrangement or micro avalanches, I mean. So with this, I go to the conclusions. So the take-home message from my point of view is that simulations are necessary to capture this kind of dynamics. We are able to do it with our TLB Fine code. And then the most interesting part from the physical point of view is that we are able to investigate the origin of this restarting of motion that cannot be captured by just looking at the equations describing the systems. So here you can find the archive version of the paper. We are still waiting for the report of referees. It has been already submitted. And here, any further details about the methodology employed. I didn't want to spend much time on lattice Boltzmann in this talk, but any details can be found here. So thank you for your attention.
These initial condition for a density packet motion.
So we prepared the emulsion by tuning the droplet diameter and the number of droplets.
I saw that you spotted dispersed, right?
Yeah, slightly, but I placed them in a honeycomb structure. Then there is a pre-run before applying the buoyancy force, where the system relaxes toward its own energetically stable state. And that's why you see that some of the droplets are smaller and so another one are slightly bigger because of this relaxation process. And then we apply, after we are sure that the system is stable, then we apply the buoyancy amplitude force.
What's the interaction between the droplets?
Yes. Yes.
Or scheme. Does it depend on the temperature, or you consider the same?
No, it does not depend on that. Yes. Please.
I could imagine I had an array of 4 drops, and I say move two of them closer and 2 further apart. That's a reversible change of the positions of the 4 drops. So it's maybe I'm confusing with the merger.
So if you have a cluster of 4 droplets that just rotate, you do not observe any kind of plastic event. You just have
say A and B apart and C and D together, but there's no merger. I could undo that.
I didn't get the point. Sorry.
The left-hand one by moving C and D points apart.
Yes, but when you are part of a huge system with you can feel also the presence of the other droplets. It's not so easy to go back in the previous, so it is not a reverse process in this sense. It's a rearrangement of droplets towards reaching the most stable configuration from the interface and structural point of view, or in terms of structural energy and interface energy.
And in the same spirit, do you think it's more the T2 transitions or T1? It's just change of makers or really coalescence between droplets?
This one counts only for neighboring switching with no coalescence. So the points I showed you before here, the dotted, correspond just a coalescence event. So they are counted in two different ways.
Like what it says that before this burst of this event, you have some kind of change of makers until it starts.
Yes. But coalescence events are observed only during heat transfer, so during the motion, while the plastic events occur also during the resting periods. Because if you have a look at the video of these dynamics, it's very visible that also during resting periods, the emulsion is moving, but only locally via plastic events, yes.
Thank you very much.
Thank you.
Next speaker is
It being recorded?
Just a minute.
Okay. Okay. I thought it would be online or something.
Fine.
Yeah, this one. Okay, so the sticker is not here. Thank you. Okay, so no, that's fine. Thank you. So good morning, everyone. So yesterday I presented another talk. This one was supposed to be a poster, but this was upgraded, and I'm happy with that. Both talks has to do with liquid crystals, but the method is completely different. So yesterday was about active kinematics, more biological stuff, and today is passive liquid crystal. And since you have to compare with experiments that we collaborate with people in USA, University of Colorado in Boulder, it's way more difficult to use the correct parameters of liquid crystals. I'll tell a bit some challenges that we found. So first, what is a liquid crystal? It is a material that has some interesting properties. It's able to flow like a liquid that we are used to, but it is anisotropic. So the particles or the molecules in the liquid crystals, they tend to align parallel to each other, so the neighbors. So the liquid crystal can be in different phases. So it can be a crystalline solid at low temperatures, and these will be arranged in a regular lattice solid. At high temperatures, it will be a normal fluid, isotropic fluid, as water, oil, and so on. But in intermediate temperatures, we have the nematic phase that is more interesting. So it flows, but it still is anisotropic. And what is a skyrmion? So this is a kind of topological defect that is formed in the liquid crystal. In the following situation. So we have two parallel plates and a liquid crystal in between. Far from the skyrmion, or usually this liquid crystal, all the molecules would be pointing perpendicular to the plate, so uniform state. However, this liquid crystal that we use is cholesteric, so it tends to form twists, something like this. So when we melt a certain region by heating with a laser, a certain portion of this liquid crystal, a topological defect is formed because its energetic configuration is lower than the uniform state. So it's energetically favorable. And here we have some figures of this of this configuration. So have in mind that this kernel is a texture. So it's not a body, it's not a capsule. I will sometimes represent just the limits of this kernel, but it should be the limits of this red region, for instance. But it's a texture. We have fluid passing through it as well. So one effect that was well studied in the literature was the behavior of this kernel when we apply electric field perpendicular to the plate. So when we apply an electric field, it breaks the symmetry to one of these directions. And well, it is pointing vertically initially, and then when you apply the electric field, it flips, it becomes horizontal to one of these direction in the plane. And when we turn off, it comes back to its original shape, but in a slightly different position. So we keep doing this, turning on and off the electric field, and it keeps moving. That's what I'm showing this in this movie. Is an effect that is quite well studied nowadays. So how this kernel moves under an oscillating electric field. This has nothing to do with hydrodynamics. It's just a texture that is moving. Our contribution to this field was to study the behavior of liquid crystal kernel without electric field, but using external flows. So what happens when we blow more material between those parallel plates? We have something close to a Poiseuille flow. And what happens to this texture? Is it destroyed? Is it deformed? So that's our question. Okay, so how we do this? We use a model for the liquid crystal. It's based on the Frankelsen free energy. It has 3 terms, one for each kind of deformation of the liquid crystal, one for splay distortions, other for twists, and other for bend. The continuum equations that you use, one is for the director field, so the orientation of the molecules, and the other one is the Navier-Stokes equation. So it has most of the term, it has all the terms of the usual Navier-Stokes equation for Newtonian fluids, plus other ones that comes from the liquid crystal theory. So we implement this, the first one using finite difference. It's a hybrid method, finite difference, and this one use Letts-Boltzmann for the usual terms. So usual Letts-Boltzmann, DTRQ-19, BGK, and the extra terms we use, we implement them as forces. So we use Gould forcing scheme to introduce these extra terms. Okay. So here we have the viscous stress tensor. It has the usual shear rate and the usual viscosity. This alpha phi is has the role of the kinematic of the absolute viscosity. And well, initially, when we tried to implement these and use the correct parameters of liquid crystal, we found some challenge because the parameters of the director field and of the velocity field, they were in completely different orders of magnitude. So we could not find a set of parameters in numerical units that made the simulation work. So later we realized why, because the time scales for the director field of the liquid crystal and of the velocity field, they are completely different. They are separated by 6 orders of magnitudes. So while we see the director field changing very slowly, we see the velocity field changing quite fast, frenetically. So well, we could think, well, if they are separated by those orders of magnitude, why not consider the velocity field to relax instantaneously? So that's what we did initially. We have a publication where we use this approximation. However, we saw a strong spurious current in this kind of simulation. So they were so strong that sometimes they destroyed this kernel. So it was not realistic. And then now we use brute force. We do solve both equations, use a very small time scale, 10 to minus 9 seconds, the time interval. And well, it's possible, but the simulation is quite slow, right? So this is work that we published last year, where we simulate this kernel in 2D. That's what we could do at that time. So because the time step is so small, the simulation takes very long, even in 2D, parallelized in 8 cores. A typical simulation takes a few weeks. So In 3D, well, it would take many months, so 6 months, 1 year, and we don't know if it would work. So we started with 2D simulations. It's a bit strange because we are approximating a Poiseuille flow by what happened in the middle. So what we do, we apply an external force to drive the flow and a friction to mimic the dissipation energy from the plates. That's what we did initially. Well, it's quite a strong approximation, but let's see what it predicts. From our simulation, it predicts that the skirmion, we have here the contour of the skirmion, it keeps elongating as it flows, and it elongates indefinitely, so until it reaches the limits of the system. And so we have here some snapshots. It becomes very elongated. We have the aspect ratio against the position, and we see that they follow more or less a linear relation. And we convinced the experimentalists to try this. It's a top group led by Ivan Maliuk. They studied these effects of the electric field when they tried injecting more material between the parallel plates and see how the skirmion deform. And then that's what they found. The skirmion do elongate. So although the 2D simulations, they are very simplified, a strong approximation, they predict this qualitative behavior of the elongation of the skirmion. Okay. Okay. And so we have here some snapshots, and we see that the aspect ratio also increases more or less linearly with the displacement of the skirmion, although the velocity is not constant because the skirmion is accelerating. It's difficult to control the velocity of the skirmion with using a syringe. But still, this relation is more or less respected. Okay. Well, what happens when you have many? So many skirmions. Well, they start to elongate initially, but then when they start to interact with the neighbors, they stop elongating, and some of them even shrink, as it's indicated by those arrows. And this is also observed in the experiment. This one start to elongate and then interact with the neighbors and start shrinking. And when we see the average aspect ratio for those skirmions in the simulations, we see that they start to elongate, and then due to the interaction, they elongate less compared to a single skirmion. Okay, but this model is very simple. There are some limitations, right? One of them is the reversibility of the shape of the skirmion. So what happens when we turn off the flow? In the simulation, when we have a kind of elongated skirmion, here is not so much, but it's kind of elongated. When we stop the flow, stop applying the external force, it becomes more symmetrical, as it is indicated here. But it keeps the elongation. So the aspect ratio is not 1 as it was initially. And if you pick up a more elongated skirmion, it will keep the elongation. And this is a consequence because we are assuming that the system is symmetrical in this perpendicular direction. What is not true in the experiment? It has a more or less losangonal shape. In the experiment, when they stop the flow, the elongated skirmion shrinks back and come back to the circular shape. So this is a behavior that was not well reproduced by the 2D simulations. And then we started running 3D simulations. This was possible due to the parallelization in CUDA. And we are now using GPUs. What increased the speed by 2 orders of magnitude compared to the previous simulations. Have in mind that those numbers are not so large, but we have to use double precision. We didn't manage to use float so far. And it's not only Let's Boltzmann. So there is Let's Boltzmann is like 5% of the code. And most of it is finite difference. So we did proper 3D simulations. It's still in a small system, but it's 3D. So we applied no slip at the walls, applied the force, and saw how the skirmion deformed. And now, in 3D, we see in the simulations that the elongated skirmion, when we stop the flow, it comes back to the original shape. It becomes circular again. What we observe in the experiments. So the 3D simulations, they are more expensive, of course, but they are much more realistic. They can reproduce more phenomena that we don't observe in 2D. Okay, and we studied puzzle flows. And now what happens in co-ed flows? When we have one static plate and we start moving the top plate. We see in this image that the skirmion deformed so far, but what happens to the dynamics? Does it elongate? Is it destroyed? Does it follow the moving plate? So in this simulation, we'll be moving the plate in the X direction. So in this one, let's see what happens to the skirmion. Well, it follows the plate, but it also has a transversal velocity, which is a bit counterintuitive. What breaks the symmetry here? Why it goes down, or why not up? This is because of the nature of the liquid crystal, because it is cholesteric. So it breaks the symmetry naturally. But to where it goes, it will depend on the separation between the plates. So in this case, it goes down, and we show analytically why it follows this behavior. But if you change the separation between the plates, it generates flows in the other direction. So again, the experimentalists helped to see if it's not just some filter of some defects of the simulation. And they did observe that the skirmion follow inclined trajectories. But in the experiment, some of them go down while others go up. We believe, we are still investigating this, but we believe that that's because the separation of the plates is very difficult to keep the plates very parallel to each other at this scale, at the scale of 10 micrometers. So probably there are some differences between this side and the other, what makes the skirmion to follow different trajectories. When we reverse the flow, it's still inclined, but in the opposite direction. So to conclude, we have studied the behavior of skirmions in Poisson and co-ed flows. In the co-ed, they elongate. In the Poisson, they elongate, while in co-ed, they fall inclined trajectories. The 3D simulations, they are more realistic, although more expensive. And there are some experimental findings that confirm our main findings. Conclusions. If you want to know more, there are those references that we published. Okay, and that's it. Thank you for your attention. Okay, that's that's not my specialty, but I think it comes from nuclear physics. I think there was a guy called something Skern, and then it was named after him. It was a name of a person. Yeah. Ah, okay, the initial condition. Okay. No, I don't have it here. I started the skirmion, I think, oh, I think maybe I have the initial condition here. It is the unansatz. So I start with a configuration that is symmetrical in the Z direction, that follows the correct topology. And then I relax this configuration that's more or less cylindrical, and naturally shrinks to this losangonal shape when you confining two parallel plates. That's it.
Would it be an option for you to solve the evolution of this director field also using Laplace Boltzmann as a kind of difference?
Okay. Okay, good question. Well, some people in the beginning have tried not in this field, but in active kinematics to solve also the directors with Let's Bolt. So it's possible. Although it's way more expensive because instead of, let me show you the equations. Well, instead of only 3 fields here that are the directed fields. You have like 19 fields, the populations. So it's more computationally expensive, and it was less stable. So well, we probably can improve, but there is no clear advantage. So a hybrid scheme was a good compromise that people found in this other field that also involve liquid crystal. But for this, I didn't try, but I expect the same.
Thank you very much.
Thank you.
This is also something I can. Or not? Ah, got it. It is working. Yeah, perfect. All right. Then a lattice-Boltzmann study of Beisel is a novel type of catalyst support structure is what I would like to talk about today. First, a bit of the main takeaways of the study that we did. The main goal was to validate recent experimental results on the improved properties of Beisel-based catalyst support structures by means of using simulations, as well as further optimization of the structures by means of simulations. And the main achievements were that the simulations show that the performance of these Beigels can be several times the performance of equivalent stochastic structures, and also that the simulations allow us to find optimal properties, optimal parameters for generating the structures. Well, but it's the motivation why we're doing all this. Well, catalysis is basically used for the production of almost every chemical at some point in its production process. And porous media are often used to hold these catalyst particles, so they're basically the catalyst support structures. And that's because of their high surface to volume ratio. Generally used commercially, structures are stochastic, and this means that they have generally poor transfer properties, unfortunately. I mean, and this in particular comes forward for gas generation reactions. I mean, as you can see here on the right, these bubbles, when they move up due to buoyancy, they get trapped in here, dead ends. They're also like dead pores here, which means a loss of surface area. They have to follow like very tortuous pathways to get out of the structure. And that's generally not very beneficial for transport through the structure. And this also makes the search for novel support structures viable. Well, one possible solution for this would be to make use of bicontinuous interfacially jammed emulsion gels, or bigels for short. And these are basically 2 fluid phases mixed with nanoparticles, where if a spinodal decomposition between the 2 fluid phases triggered, the nanoparticles tend to move towards the interfaces, and with that, they jam the emulsion. The nice thing about these structures that you can then obtain by solidifying one of the 2 fluid phases is that they are highly tunable. And also they have very beneficial transport properties because they're always percolating by definition, as well as they have uniform domain sizes and also by definition, no dead ends or dead pores. To generate these kind of structures, we make use of the lattice-Boltzmann method, more in particular, a D3Q19 lattice with BGK collision operator. I mean, like, of course, I have the following Boltzmann equation, which would be very familiar to all of you. And we make use of the pseudopotential model by Shan and Chen to trigger spinodal decomposition between 2 fluid phases. For the solid particles, we make use of DEM, or the discrete element method. And we make use of the momentum exchange coupling, which was pioneered by Lott, as well as the coupling to multiphase flows by Janssen and Harting. Well, with this all in place, we can start to simulate our bigels. And so here you can see a visualization of a bigel with a red to blue fluid ratio of 5:9, a particle volume fraction of 0.2, and also we have an equilibrium particle contact angle of the particles between the 2 fluids of 97 degrees. Well, for this 1024 cube lattice, this results in approximately 410,000 particles. And as you can see, unfortunately, the simulations are very expensive. For this case, we needed approximately 250,000 core hours on the Intel Xeon Platinum 8168 CPUs. As you can see here, there's a phase of very rapid initial domain coarsening. And then when the interface sweeps through the domain, the particles basically get trapped. And then at some point, when all the particles are, enough particles have accumulated at the interface to stop the domain coarsening, it really slows down to the point where it's basically almost inhibited. Well, with this in place, we still need to do some post-processing to get our geometries. We convert the lattice sites that have mainly red fluid as well as lattice sites covered by the particles to solid. And then we go from this stage over here to this stage. And then also because if you would push flow through it, the particles are still floating around in the void space that were basically not being trapped by the interface when it's swept through the domain. They would be flushed out normally. So we also would have to remove that in our simulations. And for that, we make use of the Horsham-Koppelman algorithm. And then we end up with these kind of structures. These structures we would like to compare to stochastic structures, and more in particular ones that could be seen as models for what is generally being used. And to that end, we make use of pseudo-randomly placed overlapping spheres, which can be seen as a model for sintered beat stochastic structures. But for every Beisel-based pore structure that we generated, we also generated an equivalent stochastic structure. And what equivalent here meant is that the surface area as well as the porosity of these Beisel-based structure as well as the stochastic structure are matched 1-to-1. When we then do a visual inspection of these structures, you can already see that they are morphologically speaking quite a bit different. I mean, like on the left here, you have a Beisel-based structure with the following properties. And on the right, you have here an equivalent stochastic structure. So for both, the porosity and the surface area are equal. Then we can, of course, further quantify this, for instance, by looking at the pore size distributions of these structures, where we computed the pore size distribution by, for every lattice node, computing the largest sphere that fits in the void space and still covers the entire node. On the right here, you can see some pore size distributions for Beisels with a particle volume fraction of 0.2, and equilibrium particle contact angles varying from 90 degrees in the blue, 103 degrees in the purple, and 170 degrees in the red. Well, here the filled markers are the Beisels, and the unfilled markers, these are their equivalent stochastic structures. And as you can see, the pore size distributions for these Beisels are generally much more shifted to the right, so they have larger pores. That holds for all the structures plotted here. And well, not only for all the structures plotted here, but in general. And what is also maybe not as well visible from this plot is that the standard deviation in the pore size distributions is also much wider or much larger for these stochastic structures than for the Beisels. In other words, for these Beisels, we have much more uniform domain sizes. Of course, we can also have a look at the permeabilities, which are defined by Darcy's law. And for this, we again employ the lattice Boltzmann method to see what how much the flow is inhibited when we push flow through. In the plots, basically to guide the eye, we make use of these dimensionless reactor efficiencies, where we postulate that the efficiency of these reactors or of these structures as chemical reactors depends on the permeability as well as the surface to volume ratio squared, which gives us a dimensionless number. On the left here, we've plotted the stochastic structures for varying particle volume fractions denoted by the markers, as well as varying equilibrium contact angles of their equivalent Beisels denoted by the particle colors. And as you can see here, for basically all the simulations that we did, they more or less appear to lie on the same isoline. However, if you also make such a plot for the Beisels, you can see that this is not really the case. And there is some kind of increase in the reactor efficiencies, especially for very, very small equilibrium particle contact angles, as you can see, for instance, for these data points here. Of course, you can further quantify this by means of reactive flow simulations that we did. For this, we again use a lattice Boltzmann method with multi-component formulation, where we use fluids with equivalent properties. Periodic boundaries on all sides of the simulation domain, where we have basically our structure in the middle, we have some void space before and after the structure to make sure the flow can equilibrate. And at the outer edges of the domain in the X direction, we have a recoloring layer where the fluid fractions are being recolored back to their initial conditions, which is loss of red fluid and very minor blue fluid. Then we force the fluid through the structure, and then inside the structure, at the lattice sites that are near solids, we convert red fluid into blue fluid with the following by means of the following first order reaction model, where basically the change in red fluid and the change in blue fluid also depends on the number of neighboring solid sites, the reaction rates, as well as the red fluid density. And we also make use of this equilibrium density, which is basically to make sure that the populations never go negative, because at the end of the structure where almost all the red fluid has been consumed, if you then also apply forcing, then simulations that go negative. So this is basically just a numerical trick to avoid that. To quantify the performance of the geometries, we make use of the effectiveness factor, which is the amount of reacted converted at steady state divided by the amount of reacted that could have been converted if no retardation was present. And that's, in this case, is defined in the following way. And here we are mainly interested in effectiveness factor improvements. In other words, like what is the effectiveness factor of the Biegel divided by the effectiveness factor of the equivalent stochastic structure? Well, so for these advection dominated flows, we reported here the effectiveness factor for a particle volume fraction of the Biegel of 0.2. And here the equilibrium particle contact angle is decreasing from blue to red. So as you can see here, for small particle, so for small equilibrium particle contact angles, we have a quite major increase in the effectiveness factor. So we decided to study this case further also for different particle volume fractions. And here you can see the plots for these particle volume fractions, where you can see that for small particle volume fraction, the increase can be even higher, up to almost 3 times. Well, that brings me to the conclusion and outlook of the talk. Well, we explored the applicability of Biegels as a novel type of catalyst support structure. And the simulations show that these Biegels can be almost 3 times as efficient as equivalent stochastic structures. What we would like to do in the future is also to look further into the applicability of these Biegels also for immiscible reactive flows, in particular these gas generation reactions. And for this, I have the following teaser video, where you can see these basically these bubbles forming and then just moving towards the structure. Well, with that, I would like to thank you for your attention, and if there are any questions, then I would be happy to answer.
How did you generate these structures? Was it just simple overlapping spheres or?
Yeah, we basically made an algorithm for these to optimize the porosity and the surface area of the stochastic structures at the same time. So it's just overlapping spheres where we then can compute the porosity and the surface area and then keep on iterating until we converge towards the values that we would like to have.
And how do you realize, or can you at all realize such structure in real life experiment?
So they could be realized, for instance, by sintering beads together, very small beads. Yes, yes. There have been papers on how to do that, yeah.
I noticed you use contact angles that are away from 90 degrees. Does that affect the stability?
So the higher the contact angle, so how should I say, the lesser the stability. The higher the contact angle, the lesser the stability, because in that case, the area that is covered by a particle at the interface is smaller, so the detachment energies are lower.
The reason I'm asking experiments, as far as I know, has been quite challenging to make Biegels if the particle contact angle is not near 90 degrees.
True, true. I mean, like we also see that in our simulations, we just try to stick as close to, well, relatively close to 90 degrees.
very much.
Thank you.
Next session is Schindler.
Yeah, I'll just need to go forward and backward. I guess.
Oh, yeah, it's just.
So I'll use this mechanical to see just the keys. Oh, great. Okay, that works great. Thank you very much for the introduction and thanks for the organizers for putting together this nice conference. Also, thanks to the previous speaker who introduced quite a bit of background that I won't need to go into details anymore. So I'm also going to talk about bigels, which are a particular class of particle stabilized emulsions. You can see a picture there and some visualization there. These systems are interesting emulsions because in contrast to simple fluids, you basically have two components, and if they demix, you have an interface between the two components. So you add the physics of surface tension to the system, in addition to density and viscosity. Plus, when you add particles to stabilize the system, you now also have another length scale into the system. So the physics become quite interesting, I think, and there are lots of things one can study in these systems. Now, I'm working in material science, and they're also engineers, and they would like us to do useful things or things they can make. So we are actually looking at possibilities of actually gaining control over how these bigel structures form. So we are going to use anisotropic particles and particles that have a magnetic dipole moment so that we can potentially control the orientation of the particles with external magnetic fields, and to explore if that's a possible way of controlling what the resulting structure of the bigel is. So before I go into details, I would like to say this is mostly work from my PhD student, Nikhil, and with a couple of collaborators in my group and at Berkeley National Laboratory, where Nikhil actually is spending his summer currently. And we received funding from the National Science Foundation, both for doing the research and also for computational resources at some of the national facilities. So from the material science perspective, emulsions are interesting because there are actually processes based on emulsion templates to make materials. So the idea is you take a mixture of two fluids and you somehow control and move them into the phase separating region, for example, by solvent transfer or solvent evaporation. So the mixture begins to separate, and then you use the structures that emerge from that separation as a template to make a porous structure, for example, by solidifying one of the phases. So this is a very common technique, and it gives rise to interesting opportunities, I think, to use liquids in material science. Bigels, as we have seen, are a particular structure. They are similar to Pickering emulsions, so when you have particle decorated droplets, but here the structure actually forms during spinodal decomposition of the two mixtures. So you have these large interfaces forming that then start collecting the particles, and at some point the particles jam and arrest that structure. Now the phase diagram is actually fairly narrow where you can actually get the bigels. So experimentally it's a little bit challenging to actually get to those, and I'll come back to that in a little bit. All right, so here's an image which you've seen already. So from the applications, we are particularly interested in tuning the transport properties. So there are applications, for example, in drug delivery systems, where you use some of the phases that have formed as channels for transport. So depending on the morphology of the bigel, the transport properties may change. This can also be used in liquid-liquid extractions, where you use actually bigel fibers to maximize the interfacial area to separate different components. So in order to improve these applications, we would like to get control over the structure that forms. And the idea that we followed is that if you use anisotropic particles, you get additional interplay between the interface and the particles, because if you have non-spherical particles, it's already not possible to put it onto the surface without inducing curvature of the surface. So there will be capillary effects. And if you now are able to rotate the particles, you start actually deforming the interface even more. So all kinds of things could happen. So the idea was, if we use magnetic fields, for example, to rotate the particles, can we control what happens during the formation of the bigels? And we did that with similar methods as we have already seen. So we used the Shan-Shen multi-component model here with a non-ideal equational state. We have some interactions to control the contact angle. So this is all very similar to what the previous presentation showed. We also use what most people call the lead coupling to have the particles on there. We also include lubrication corrections at short distances. So when the particles are fairly close, the hydrodynamics might break down, so you need to correct for that. And we have all those interactions in there, including the contact angle, although in the results that I'll be showing, we have used a contact angle of 90 degrees throughout. So the setup for a simulation is like this. So what we model is actually small particles of micron size with a permanent magnetic dipole. So it's not ferromagnetic particles, but permanent dipole particles that have about a dipole strength of 3 × 10⁻14 joules per Tesla. So in experiments, that would mean you need magnetic fields on the order of millitesla. So that can potentially be achieved, although nobody has actually done this in reality so far. What we do then is basically we quantify the magnetic field in this dimensionless form, which is, you can think of this almost like a Bond number. So it relates the magnetic field to the surface tension effects, essentially. What we measure then in these structures is the so-called structure factor. So we take the Fourier transform of the deviation of the order parameter. And well, that allows us to calculate certain properties like a domain size, for example. This has extensively been studied in spinodal decomposition. So one thing that we found actually during the analysis is that if we plot the structure factor S of k and t in wave vector space and scale it with the domain size that we have obtained, we get actually a pretty good data collapse. So that goes back to this idea of that it's challenging to form bigels. What this means is essentially the formation is still mostly driven by spinodal decomposition. So adding the particles does not fundamentally alter the mechanism with which the phase separation occurs, which is, I think, interesting because it suggests that experimentally this will not be a problem. Now, what's more relevant then is actually the domain size itself. And if you follow the spinodal decomposition literature, there's plenty of ways to measure a domain size in these structures. So L1 here is the one that's obtained from a spherically average structure factor, and that's maybe the most commonly used one. And if we look at the scaling, we get exactly the same scaling as we get in inertial decomposition for spinodal decomposition. So that also confirms. Well, there are other measures, for example, from the second moment of the structure factor, which behave a little differently. So there may already be some effects of the particles visible if you go to higher moments of the structure factor. But generally, we have good agreement with inertial scaling. One advantage of using the second moment of the structure factor is that we can do that independently for different directions. And that's where things start getting interesting because we have anisotropic particles, and indeed, this leads to anisotropic structure of the bigel. So the domain size, if you look at different directions, is actually a little different. So this means the transport properties would also become anisotropic, and there may be interesting applications to do that. And what we found is that the directionality that we see depends on what particle shape you use. So in this plot, for example, we show the spherical particles are the black ones. That's the reference case. The particles with alpha equals 2 are ellipsoidal elongated particles with aspect ratio 2. And the blue symbols are for ellipsoidal particles with an aspect ratio of 1/2, which means they're disk-like, right? And the magnetic dipole is always oriented along the symmetry axis of those elliptical particles. What we can see is that the structure differs depending on what the particle shape is. So this may be one way to have control in experiments. And we can also see that there is a slight dependence on the magnetic field strength. Another property that sort of porous media applications are relying on is what's called the tortuosity. So that's how curved the path through the material are. So here we also see the anisotropy, which is interesting for applications like the transport applications, because if the paths are more curved, that might require higher pressures for filtration applications. So some applications would demand a lower tortuosity, while other applications rely on a certain tortuosity. For example, there are battery materials where the tortuosity has been linked to dendritic growth and the aging of the battery electrode. So being able to control this to some extent is a promising direction. Now, in order to understand why that's actually happening, we looked at the particles themselves. So one thing we measured is the nematic order parameter of the particles, S here. And what we see is, not unexpectedly, the particles align with the applied magnetic field. But if we look at the nematic order parameter over time, we actually see that's non-monotonic. So it starts increasing as the spinodal decomposition starts. And then there is, depending on the field strengths, a decrease at some point, after which it increases again. So, and the way to understand this, we believe, is that there's an interesting sort of cascade of things that happen. So initially, there are not a lot of interfaces in the system because they just start forming. But the field aligns the particles. So there's not anything that works against the particles. So they start aligning, but then the interface starts forming and moving through the system. And the surface tension is relatively strong. So it's able to pull the particles a little bit away from the magnetic orientation. And then after some time, the interfaces have fully formed and slowly coarsen. Then the magnetic field can help to align the particles which pull the interface along. So we eventually get also an alignment of the interfaces themselves. Now, in terms of how this is happening, and I think this supports a little bit that mechanism, is if we look at the coarsening speed, like how fast the interface starts growing, then in comparison to the field-free case, the black curves, we can see that depending on the particle shape, in certain directions, the growth is prolonged, essentially. So if you look at, probably should use this pointer, at this part here, that we see in the direction perpendicular to the symmetry axis, the velocity, there's a velocity that lasts longer than in the other directions, and in the case compared to without a field, while in this case for the prolate particle, that's actually reversed, but there is a direction where the domain coarsening proceeds for a longer time. And that makes sense with this idea of having the interfaces more aligned. It also suggests that there is some reordering of the particles in the interface. So we look at, okay, this shows it visually. So here we look at both the domain size and the nematic order parameter. And so initially we see kind of a random orientation of the particles in the interface. Then due to the magnetic field, they start reorienting, which frees up a little bit of interface occasionally. So, and then that interface would like to coarsen. So that area will kind of disappear by shrinkage. And that forces more particles to align. And you get a structure that eventually looks like this. So there's a fairly ordered structure in the interface of the particles in the end. And that's something we are still investigating. We'll look at further into that maybe in the future. Because currently what we can measure is, orientational order and radial distribution function in 3D. What we're trying to do is kind of to measure the radial distribution of particles in that interface, which is embedded in 3D space. So it's a little bit more difficult to do the post-processing. So one other thing, of course, that you can ask now is this was observing how the bigels form when a magnetic field is present. What can we do if we already have a bigel and then we change or switch on or off the magnetic field? So that is something, it's not advanced, or there we go. So that's something we are working on at the moment. So we already have a bigel that has a certain amount of order in there. And for example, we start with a relatively low field, and then after the bigel has formed, we increase the field. So the first results that we have show that there is still slight changes that are related to the strength of the magnetic field, but the most of the changes happen actually during the formation. So it's easier to create structures during that initial spinodal decomposition. Once things have arrested, it turns out to be a little bit more difficult to actually change things. Now, one thing that's interesting about this, that things do depend on how you process the material, and that's always an interesting thing to understand for materials processing. So yeah, here we can see basically how that depends over time. So the domain size changes very little depending on what the initial field was, but there are still some changes in the nematic order. But again, this is somewhat preliminary and we're still analyzing this. So yeah, let me summarize. What we have seen is that the domain size in bigels and the orientational structure can be influenced with particles that are anisotropic and respond to an external magnetic field. So what we've seen is that the domain size and the tortuosity become anisotropic, which may lead to interesting transport properties in applications. We have gained some understanding of what's happening. So there is particle realignment that couples into interfacial alignment and ordering. So these structures that we see with the particles may also have actually interesting optical properties for materials. So there may be another thing to explore in the future. But sort of the bottom line is that with these simulations, we can actually test certain new fabrication techniques, understand what's happening, and then hopefully assist experimentalists in making better materials at some point. So I think that's what I wanted to tell. Thank you very much, and I'm happy to answer questions. The particle dynamics, yes, okay. So it's essentially a lead coupling. You familiar with that? So we have a bounce back boundary condition for a moving boundary. Right, so the particles are solved with molecular dynamics, if you want to look at that. So each particle has a position, an orientation, and a velocity and an angular velocity. So we update that in every time step. And then the interaction between particles and fluid is done by imposing boundary conditions on particles or links on lattice that cross the interface. Yes, yes. The liquid interface, oh yes, so that's emerging actually. Because, well, so I have to probably explain a little bit more. If you have a multi-component fluid here, you do that bounce back for each of the liquids, right? So each side can be occupied by both types of liquids, right? Depending on what the interactions between the liquids are, there may be one phase present here more than the other phase, right? So you have maybe red fluid here and blue fluid on this side. Right, and then there's also an interaction between the first layer of nodes in the particle and the particles outside, which is similar to a Shan-Shen type interaction, that is used to control the surface tension. So if there was an interface somewhere, well, the particle would either move up or down in that interface until it adjusts to the contact angle that we have set with the parameters. Yes.
Thanks all for it.
Yes.
I was, if you have seen, so if there is some dynamics in the, so once that the particles align, they remain aligned, or is there any type of?
They remain mostly aligned, but again, as I've shown in the nematic order parameter, there is this intermediate state or regime where the nematic order decreases again. And that, I think, is because, well, first of all, the system is fairly inertial. So if an interface has formed and is sweeping through the system, right, it can, collect a particle that is aligned with the field, but then the interface is kind of not aligned with the field. So it may pull that temporarily out of the alignment. But then later on, because the interface is somewhat mobile, right? So then the particle can slowly pull that interface back into that aligned direction. That's our explanation for this data. So. Great question. We haven't done it yet, but it's on our list. Yes, yeah. As we. Yes, so the rotating ones we haven't looked at yet. The ones we're trying is gradient fields, right? If you have a field gradient, because that might move particles in certain directions. Rotating might be interesting for mixing or something like that. So that's, yeah.
Do you see particles extruded from the interface, or they remain there?
Another great question. Occasionally we see people, particles being expelled from the interface. People, no, it's not particles. Yes, yeah. Right, so yes, that can happen because the compression sort of in the interface is not small, right? Yes, exactly, right? So that can happen. It typically happens during sort of pinch-off events or coalescence, right? That's when the largest rearrangements happen. And occasionally, particle is pushed out of the interface and then may remain, but it's very few. It's like 1% or so. Yeah.
If these particles become very close, then the gradient and lubrication correction should also become very high. So how do you?
Right. When the lubrication force becomes very large? Well, it's so the volume fraction we used here is 0.15. And at that volume fraction, we are able to simulate it. It becomes challenging if you go to the 0.20 and so that you would have to change your parameters so that effectively your time step is smaller. That's the only way to resolve those larger forces, right? Because the forces are physical, right? So the only way to resolve it, reduce the time step, which in lattice Boltzmann you would do by adjusting the viscosity essentially, right? So, or the relaxation parameters. But then again, as you probably know, in the Shan type models, there's a lot of things that change at the same time, including the surface tension. So it's a little tricky.
Thank our speaker and all speakers.
Right? Yeah. Thank you.